Now, the early universe developed these stars, and we call those first generation stars. And many of these were probably 100 to several hundred times bigger than our star. And these enormous stars go through their hydrogen fuel much more quickly than a star like ours, which is kind of a medium or smaller star. But once they use up so remember, they're fusing hydrogen, they're making heavy elements, and they make elements, they make carbon, oxygen, nitrogen, sulfur. In fact, what did we talk? We talked about those chomps, right? Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, right? So those are the chemical elements of living organisms, right? So those were really made inside of stars, because remember, the Big Bang only produced basically hydrogen. Everything else had to be produced by nuclear fusion inside of a star, right? But eventually these big stars are so massive that they just implode on themselves, and that's what we call a supernova. So during a supernova event, elements that are heavier than atomic number 26. So remember, iron is atomic number 26. And what atomic number 26 means that there's 26 protons in the nucleus of iron. So inside of a star can only make chemical elements up to iron. It can't make anything heavier. But we have gold, we have silver, we have uranium, which are much bigger atoms. How do they form? They form by a supernova event. The supernova event is important for two reasons. One is we're making these elements heavier than iron. And second, we're shattering this heavy atom object into space. So basically, this heavy atom object is going to be the seeds for solar systems and planets, right? For planet Earth, for example, right? So your book makes a point of a couple of things here. So there's this Big Bang nucleosynthesis. So that's the production of hydrogen and helium, maybe some lithium there, some really light elements. Then we see stellar nucleosynthesis. Well, that's the nuclear fusion, right? And remember, that only goes up to iron, atomic number 26. Another thing that we can make a point out is Einstein's equation here. Energy equals mass times the speed of light squared, right? So when you fuse, so the M term is important. That's mass. When you fuse two elements, you're changing that mass and you're multiplying it by an enormous number, the speed of light, which is squared. And so basically this E equals mc squared is what occurs inside of stars. It gives us the energy. Well, in fact, that's our external heat engine, solar radiation, right? Now, as we go along here, our star may be a third, fourth, or maybe even a fifth generation stars. So the planets, the rocky material, the heavy atom objects in our solar system really are the products of other stars that have lived their cycles, right? Have gone through their nuclear fusion, and especially the big ones who have gone through supernova and spread these heavy atom objects into space, right? So the question science, especially in cosmology and in physics, what they've determined is that the atoms that make up our planet, that make up our bodies, at some point were inside of a star, right? So like Carl Sagan said, we are stardust. Now the next part here deals with the formation of our solar system. And so it comes from the solar nebula. In fact, they call it the nebular hypothesis, right? So we have this nebular cloud. So when something's nebulous, it's not quite formed. It's starting to form. And so what's going to happen here, after a star lived its cycle, went through supernova, it spread out gases and heavy atom objects into space. At some point, this mass is going to start to condense due to gravity. So gravity is going to start pulling this thing together, right? And as gravity starts pulling this thing together, we need to talk about this thing called conservation of angular momentum. And there's an equation. So this PA term is a conservation term, which means it cannot change. We have mass, so that's the mass of this solar nebula. Whatever it started with is what we have today. It has a radius, it has a diameter, right? And then the spin is how fast it's spinning, right? So as gravity starts pulling this thing together, the mass is not going to change. But the radius gets smaller because this thing starts compressing down, right? So the radius gets smaller, which means in order to keep this conservation number the same, the velocity of spinning has to increase. So this explains how the solar system really kind of is brought together by gravity, starts spinning due to this angular momentum, and that's why all the planets orbit the sun in the same direction. And in fact, we'll watch my little video that I made that also shows this.
As well as this idea of conservation of angular momentum, and that's basically the spin factor, right? So I'm going to stand on this instrument that allows me to spin. So when as like an ice skater, when I start spinning, I'm going to have a larger radius or diameter, but when I bring my arms in, I should spin a little faster. So I'm going to start off slowly, and then a little faster than that, and then bring it in. You can see how much faster I go when I bring my arms in, when I reduce my diameter or my radius.
Well, see, that explains the angular momentum and how our solar system formed into these disks, right? So that shows how the solar system is forming. And then, so remember the lighter gases, the hydrogen starts condensing in the center to make the protostar and eventually our sun. And remember that gravitational energy is being converted to thermal energy, right? And but rocky material starts filling in the orbits, right? So the center of the nebula disk glows with heat and ignites into nuclear fusion. That forms our star. But the dust, which are the heavy atom objects, in the rings begin to coalesce to form these things called planetesimals. So planetesimals are small, heavy atom objects, usually, you know, maybe 10 to 100 meters, maybe a kilometer in size. So they're small, but they start kind of attracting to each other, maybe through electrical activity, you know, electrical charges. And then if they're moving slow enough, gravity might bring them together and they might start clumping together. As these planetesimals clump and clump and clump together, they get larger, they get more massive, and they attain more gravitational power, which they can pull in other objects, right? So this process of clumping together is a term we call accretion. So accretion of planetesimals eventually leads to formation of larger bodies, eventually form these planets, right? So here's a little asteroid, a little meteorite here, a part of a planetesimal. But see here, we start accreting planetesimals, making them bigger, and at some point, the planetesimals get so large that there's thermal energy that's, you know, causes the center to kind of mold and meld. The interior heats up to the point of melting, and then the body becomes spherical due to gravity, right? Gravity pulls everything towards the center. And then early in Earth's history, as the planet is forming, remember there's one important definition for a planet. A planet must clear its orbit. In other words, if there's any rocky debris at the same distance from the planet to the star, at some point that rocky debris will be assimilated or incorporated into that planet through collision events, right? And so in the early history of the solar system, there might have been one or two other planets at the same distance planet Earth is from the sun. And we're about 150 million kilometers from the sun, which is one astronomical unit, right? And so in order for Earth to become a planet, it had to clear those other bodies. And there's the hypothesis in terms of how the moon was formed is by this process. So the idea is that in the early solar system, a Mars-sized planet collided with Earth, right? And this Mars-sized planet had a crust, or at least a mantle and a core, right? So it had an iron core. And some lines of evidence that support this hypothesis. One is that the moon, we've been to the moon, we have rocks from the moon, and the rocks from the moon are slightly younger than 4.57 billion years old. They're more like 4.4, a little bit more than 4.4 billion. So they're slightly younger than the rest of the solar system. So it means that the moon formed at a later event. The other thing is that the moon, number two, the moon has very little to no iron core. So, for a body that size, it should have differentiated to have an iron core. So there's really very little to no iron core in the moon. And third, the moon is primarily composed of mantle material, right? So those three lines of evidence suggest that when Theia, this Mars-sized planet, crashed into the Earth, the impulse energy from Theia caused the core to continue on and meld or join Earth's core, and then the rocky material or mantle material of Theia started orbiting the Earth, and that coalesced to form the moon. A fourth line of evidence that people cite as well is that Earth's core, Earth's iron core, is considerably large. It's if you look at Venus's core and Earth's core, Venus being about the same size of Earth, Earth's core is about a third times bigger than Venus's. So that's another line of evidence. But anyways, here's a hypothesis for formation of the moon from collision of Theia. And then over time, as Earth cools, we're going to see outgassing. The outgassing produces the atmosphere, primarily in terms of water, but that water rains out, eventually fills in the low areas or ocean basins to where we form today. So we'll find that most of our atmosphere did come from outgassing. And outgassing is basically gases coming from within the planet. And most of those gases are carbon dioxide and water. Water obviously precipitated out to form oceans. Carbon dioxide dominated the atmosphere. Obviously that changed as life developed on Earth with plants and algae producing photosynthesis and changing that composition over time.